Welcome back. Today we're going to solve the 2D heat equation by using the GPU to speed up the computation. And in the end, we're going to arrive at some nice animations that you can use for arbitrary initial conditions. Yeah, okay. This video will generalize some methods we derived last time. So if you haven't watched that, go check that out. I'll put a link in the description. Okay, so yeah, let's start. The 2D heat equation just adds a second derivative term, where in the last equation we just had the second derivative in x. Now we also have the second derivative in y. And if we have our two spatial dimensions, we have to introduce a second spatial index. Like, yeah, now we have an ij. In the last video, we just had an I. And we also have to use two central differencing schemes for the second derivatives, one in the x direction, one in the y direction. And yeah, if we then further assume that these both directions are equally spaced, we can derive this formula where r again is just a prefactor that sums up all the constant coefficients. Okay, so again, like last time, we're going to start by some imports. Of course, we're going to use NumPy. Like last time, we're going to build sparse diagonal matrices, so we're going to use the Derive method. And we're going to use iterative solvers for linear systems other than last time, because now these matrices are getting really big. So we're going to need to import some solvers. Yeah, that's just a gradient descent solver. Okay, and first of all, we're going to set a value for constant r. We're just gonna go with 0.5, and we are gonna use 500 points in x direction and in y direction to get a nice resolution. Okay, now that we have our preconditions set, we're going to think about the Crank Nicolson scheme. If you can remember from last time, the Crank Nicolson scheme can be simplified or can be written as a linear systems of equations where we get two tridiagonal matrices A and B that give us the derivative operators. But that was for one dimension. Now we have to think about how that will work out in 2 dimensions. How we do that is we have here a semi-implicit scheme, so we again sort out the n+1 terms on the left-hand side and all the n terms on the right-hand side. That yields this kind of equation, and now we want to write it using matrices. So therefore, we're going to switch to a whiteboard, and I'll explain how that works. So now that we have our whiteboard ready, I brought you a little sketch of our grid that we're going to solve the heat equation on. Yeah, it has indices for x and y directions, and yeah, we're going to first of all think about the second derivatives. If we have a look at the second derivative in x, that is going to depend on uij and on the following cell and the cell before in x direction. But since we have not only the derivative in x but also in j, this is going to depend on the cell before and after, but this time in y direction. And what we're going to do is, if we're solving it in a computer, we are going to flatten this whole array, giving us a huge vector where these are flattened. So we have in the first entry is u11, then we get u1n, then we get u21 up to u2n, and finally at the end un. If you think about the equation that we just derived for the matrix A, I just wrote it down here for you. We have a matrix that depends on the previous and the following cells in I, and the previous and the following cells in J. But since we flattened this whole vector, this isn't going to be a tridiagonal matrix, because we have to think about the adjacent values in I and in J. So this is going to be a banded matrix, and we have to find out where we have to, or how we have to space the diagonals in this banded matrix. And what you can think there is these three are going to stay adjacent to each other, since if we flatten them, we just place this cell next to this cell, and yeah, there we don't change anything in the x derivative. For the y derivative, however, there are exactly n cells if we have n cells in each direction. There are n cells between this cell and this cell. So we are going to have a sparse matrix that is tridiagonal for the x derivative. Then there are going to be many zeros. And then there are going to be two off diagonals, where the distance from the main diagonal to these two off diagonals are going to be exactly n steps. And now we're going to implement that in Python. Now we're back in our trusty Jupyter notebook, and we're trying to create this matrix that we just derived on the whiteboard in Python. So what we're going to do is we're going to create a list that contains the diagonals that we later on want to space in our sparse matrix. But this time it's going to be 5 entries, so yeah, we start with the easiest one, that's just the main diagonal. If you have a look at this this equation here, that's just going to be 1 plus 4 times r times ones, and now we have to think about how many ones we have. If we flatten our grid out and we got n points in x and n points in y, then in total we have n squared points. And yeah, this matrix is going to be applied to all the grid cells, so we have to use n times n values on the diagonal. Now for these off diagonals, or two first off diagonals, we have to again use ones, but since the off diagonals, it's one value less. So yeah, we're going to n squared minus 1, and again okay, now we have to use this last off diagonal term, and there we have, they are n away, so it's going to be n squared minus n entries on this diagonal that you can just derive by geometry basically. Okay, now that we have our diagonals, we have to create a sparse matrix, And again, like last time, we're going to give the diagonals and we're going to give the offsets from the main diagonal. And yeah, in the first value, we have the main diagonal, so that's going to be an offset 0. Then we have the two first off diagonals, so that's -1 and the 1. Then we have these far off terms. They are going to be n and -1/2. And for a solver, it's going to be good if we use a certain format to store it, so we're just going to give it here in the constructor. So let's have a look at what this matrix actually looks like. Okay, so now we can see why this is so important to use sparse matrices. If we wouldn't use a sparse matrix, we would need very much memory. And just to show you how it would look if we had enough memory, I'm going to make the grid smaller that it fit into memory. And yeah, again we see, I think I have to make it a little more smaller. Yeah, now you can see the diagonal and here the first off diagonal, or the term that comes from the y derivative. Okay, so now that we have the matrix we're going to use to iterate, we can think about the initial condition and the boundary condition. For the initial condition, we're going to use two hot blobs in the middle of our grid. For the initial configuration, we are going to use SK image to draw two circular hotspots on our grid. And yeah, then we're going to use a bit mask to actually write the arbitrary values to these hot points. So how we do that is we import import disk. And how the disk method works is, in the first element we give it the center in x and y, and in the second we're going to give the radius. Since we want to fit two disks on there, we're just going for the main diagonal, for the middle line, and since we want two, we're going to give it a radius of n/4, not a radius of n/4, but we're going to space it in n/4 and 3n/4 so that they are not overlapping. Yeah, since we want our array indices to be integers, we need to use integer division to compute these. So yeah, we're going to place it in y in the middle and in x at 1/4. And the radius is going to be 1/15 to make it not too big. And this is going to give us a mask, but it didn't. One sec, let me check. Oh yeah, okay, now I'm back. Yeah, it turns out I had the size of our grid too small, so that the integer division just didn't yield any integers apart from 0. Now we have the integers, or the indices in x and in y. We're going to want to write our values, and we're going to create a mask from zeros and going to set the values to 1 where our disk is. Okay, so now we and if we have a look at our mask right now, that yields one circular area where we can later on set our initial temperature. But since we want 2, we're going to copy that and are going to place it at 3 times that. And now if we have a look at our mask, we don't need to update it and create it anew. Yeah, now we have 2 areas where we have initial temperature and elsewhere it's just going to be 0. And yeah, our boundary condition is going to be 0 everywhere, so we don't have to think about boundary terms. Yeah, now we can think about our values, or we can initialize the values on our grid. That's again, we're going to start with an n by n array and are going to set the values that we just selected with our mask to. So if we have a look at this array, it's going to be a huge array, 500 by 500, and if you have a look at this, it's obvious that on the 4 edges and 4 corners we're going to have zeros, but in the middle there are somewhere these terms we just set to 10. And yeah, since we'll have to flatten it for our linear systems of equations, we can just flatten it right here. Making it a 1D vector. Okay, now that we have our initial configuration and our boundary conditions set, we have to think about the right-hand side, where we have this matrix B. Again, they're similarly like we, here, this matrix M. Similarly like we did in for the matrix A, again, we're going to take this here, and the only difference is that the spacing is going to be exactly the same, but the main diagonal is just going to be a negative 4r, and all other values are going to be just r. So yeah, how we do that is, again, we can just copy the diagonals and make it here to just noticed that here I wrote 1 minus 4r, but it should be just minus 4. Yeah, okay, so we have minus 4r, and then all these others are just going to be r. And again, we build our sparse matrix by zero, negative n1, negative n, and okay, now that we have our both matrices, we can think about solving it. So first of all, we're going to solve it with Scipy to have a comparison how fast it's going to be with the GPU, and we're going to time it later on anyways. But first of all, we're going to use it, solve it using Scipy. So first of all, we have to set our steps, how many iterations we want to have, and we have to store our results like last time. So again, we need our storage. So we have n steps, and for each step we want to store an n times n grid. So yeah, we write our storage, then we set, or we save our initial condition. Remember, since we flattened it earlier, we have to reshape it here. And now we can iterate. What we want to do is we want to solve it and in place update our values. And we're going to use the CGS method that uses on the right hand side matrix A, just A, and on the left hand side the inhomogeneity, that's just m times u, but since we just want the a vector, we can multiply it here directly. Yeah, and it's going to give us a tuple, but only the first returned value is going to be important to us. So yeah, we directly unpack it and store it. And yeah. Yeah, now that, and that's all. Now that we have it, we can just run it, and that's going to take a while, so see you in a bit. Okay, so it just finished. It took about 24 seconds, but we only simulated for 3000 steps, so if we wanted to use larger systems, 3000 would be on the lower end, so you can see that it's going to be really important to make this fast. So what we do is we use QPy, that's an in-place replacement for NumPy and Scipy, and simply runs most of the Scipy and NumPy functions, but on the GPU instead of the CPU, and therefore speeds up the computation significantly. So yeah, we start by importing QPy, and yeah, what we need there is we need to import the linear algebra library for sparse matrices, and we need to import sparse libraries. And then it's going to be really easy. We just copy the values from our initial sparse matrix. I'm going to create a sparse matrix on our GPU. Matrix. And now we have two matrices on our GPU. Of course, we have to also copy our values to the GPU, since otherwise we would have always to transfer the values from the GPU to the CPU, and that's going to be really slow. So we're going to do the exact same thing as we did here, but we're going to replace all NP with all CP everywhere, and all these API calls have the exact same signature. That comes in really handy. Yeah, okay, let's have a look at our arrays. Again, yeah, we have here a sparse matrix that we can look at. Can try if we get if that works, but probably that's going to be an out of memory error, just like before. And yeah, the values array is going to be really boring because it's all zeros. Okay, now we want to know if it's actually that much of a difference if we use the GPU or if we use the CPU. And what we do there is we use timeit to find it out. I'm going to use the iterative method CGS for that. And that's going to run a while. And we find that it takes about 74 milliseconds per run. And if we do the same thing for the GPU method, it's going to need hopefully far less. Here you can see it takes way less. And if we were to double the size of our grid, then the GPU is going to scale way better than our CPU. If that isn't working for you, you might need to have a look at the installation of CuPy. You might need to install some CUDA libraries additionally for the GPU to outperform the CPU. Okay, now that we have have timed it, we can run our iterative solver, and again it's going to be the exact same like above, only that we have to replace these function calls with the GPU versions. And if we store it, this array is going to live on the CPU, so we have on the GPU, so we have to get it back on the CPU to save it in a NumPy array. So we have to get it. And yeah, if we run that, I forgot some. Of course, we need to use the CuPy. We need the CuPy library. Okay, I don't know what that is. Let me have a look at it. Okay, so now it works. I forgot to rerun the flat command to match the sizes. So now we can run it. Yeah, it took like 10 seconds, and now we can visualize the result. Like last time, I don't really want to go into the ins and outs of matplotlib, so I just brought you a little script here that creates an animation and writes it to a file, and we can run it. It's going to take a while, and at the end we're going to arrive at the animation that I showed you at the beginning of the video. Okay, so it came back, but it doesn't look like it's very plausible, the result. So I think what I did wrong is for here in this matrix, there actually should be a 1 minus 4r, because if we look at this equation here, we get for the uij at time step n, we get minus r times 2 plus minus r times 2 is yielding minus 4 times r times uij, and we get 1 from the temporal derivative. So in the end, it actually should be 1 minus. And if we run it again, now it's going to yield the correct values. Okay, so the animation just came back after 40 seconds. And if we have a look at the animation, yeah, it's exactly the one that we got at the beginning of the video. So yeah, hope you enjoyed it. If you enjoyed it, please leave a link. So if you enjoyed it, please like and subscribe, and yeah, see you next time.